Okay, so we talk about hashing. Okay, so there are many applications and algorithms which require dictionary type operations. Okay, like on a large data set, you want to insert, delete, search some record. So these are mostly called dictionary type operation. Like in compiler, there are multiple symbols, and corresponding to that, you need to, for the key, you need to find the corresponding symbol. So this is called a symbol table problem. Consider a table S which holds n different records. Okay, and they will have operations like insert S X. So in the table S, you insert a record X. Okay. Um, then you want to delete a record from the table. So the sets will remove the record X. You want to search a record with a given key. Okay, it will return the record if the corresponding record with its key is present in the table. Otherwise, it will just say nil. Okay, that there is no such record exists if no such item exists. Okay, so. So these are all dynamic set operations. They change, the table actually changes with all the insertions and deletions of records. Now, the symbol table is used heavily in compilers, and there is a concept called direct address table. Okay, direct address table is very much like an array. Okay, so if you have an array, so if you have number 1, 5, 9, 3, 2, and you have this index positions, 1, 2, 3, 4, 5, and you want to find some element, you want to search some element. Suppose you want to search element, and this is an array A3. Okay, if you want to do A3, then you can go to this element directly, and the search time will be very less, constant amount of search time, because you are giving the index. So the index itself helps you to find the position. Okay, so now you consider you have a set of elements, a large number of elements, and you have, suppose, n number of elements, and you have an array with n positions. Okay, it's 0, 1, 2, 3, up to n. Okay, up to n, and then this elements, n number of elements are actually 0 to n. Okay, 0, 1, 2, 3, and up to n. Now this element 0 can go to the location 0, index position 0. Element 5 can go to the index position 5, and then similarly element n can go to the index position n. So in that way, it is possible. This is called a direct address table. That means the address itself is serving as the key value. Okay, so what does it say? It says suppose the keys are drawn from a set U. Okay, it's a universe of keys, it says, and the U is 0, 1, 2 up to n minus 1. Like I said, that the elements, n minus 1 elements are 0, 1, 2 up to n. Now assume the keys are distinct. Okay, every key appears only once, we can assume, and then we set up an array corresponding to those elements, the key values, so t0 to m minus 1, to represent the dynamic set as S. Now tk equal to x if x belongs to S and key of x equal to k. That means in the position of tk, we go on the key actually serving to find the position. Okay, so the key of the position x will be stored there in the position if x is in the table. Okay, like 5 will go to the location 5 in that way, and if there is nothing in location 5, that means the element 5 does not exist. Now this operation takes, as I said, theta 1 time, constant time. The key is, the indices of the array will tell you the key is present or not. Okay, and they will serve as the key itself. So but there is a problem with that. If this set, this u is 0 to m minus 1, this number of elements is actually small, it solves the purpose. But if it's a very, very large table, where the table itself cannot be stored in the memory by the memory, the real estate cannot fit the table, and then it is a problem to store, create this kind of array. And moreover, this is a possibility that you create the universe. The set is actually so large that you create the table maybe 2 to the power 64 elements or something like that. But actual element you are storing, actual like this number of keys you are actually storing in the table are very small. So you are kind of wasting the remaining space which you are not storing. So we need an innovative structure where this direct addressing kind of concept is there. The position 2 will have the key 2, but it will not need to be encompassing all the elements in the set of the universe. So that's why we say that this kind of direct address table have limited practical usage. Okay, as m-1 can be a huge number. Okay, it can be a very large number, and then you cannot create such a table in the memory location provided by your computer. So huge number to store the set while drawn from 2 to the power 64 number set. So this is a important concept. The direct address table is helpful because you can easily find the position of an element given by the index position, which is also serving as the key, as the keys are distinct. And if there is an element 2, then you will go to the index position 2 and check if the element is there or not. So if x belongs to S and the key of the element is the same, then the key element is there. Otherwise, there is nothing. Okay, the position is empty, and there is a number 3 cannot go to that position. Okay, it's just reserved for 2. So you can assume that if 2 is not in the table will have nothing in that position. So now with this background, we'll start with the hash table and see how hash tables can address this problem, to strike a balance between the space, the universe of keys size, and the actual number of keys which being stored in the table. So as I said, that some places the direct address table is not good enough. Okay, so direct address table needs you to have the table size equal to the size of the universe, and the universe can be very large. And among this universe, maybe only a handful of keys are being stored in the table. Then why create such a large table? In that case, we come up with the hash table. Okay, so hash table can solve this problem. What does it do? There is a hash function h which maps keys randomly into slots of table T. You can see the randomly here is within quotes, because this is not really randomly. It's more like a pseudo random, the feeling of random generation, that any key from this set, this is a set of elements in the so there can be multiple other key. The entire key space is U, and the size of the key space is mod U. But here there is only the element which are actually need to be stored. So I can store this one here in this slot. I can store this one here in this slot. I can store this one here in this slot. In that way, they can go to different slots. Okay, so it's not necessary to be consecutive or anything. They can go to any slot, and the slot is determined using this hash function. Okay, so what we say that when the set k of keys stored in the dictionary is much smaller, okay, this is much smaller than the set of the universe, than the universe U of all possible keys, a hash table requires much less storage. Okay, we do not need to create a table of the size of the universe. We can just create a table of the size of the number of keys currently we are seeing, maybe a few more, and then direct, instead of a direct access table, we can just use a hash table. And that so if direct addressing stores, as I said, that the index position is actually serving as the key. So direct addressing stores element with key k in slot k. Okay, so the key k will be only coming to the slot k. So because it cannot go to any other slot, it's direct addressing. The address itself is storing the corresponding key. So but the hashing stores the same element in h of k. That means we generate the hash value of that key, and whichever be the hash value, that will be the corresponding slot for that element. Okay, so there is a chance that the two elements hash value will match. Okay, so there is a chance that this element actually, this element actually maps to a slot which is actually the same slot. Okay, here two elements are being matched. Okay, one is this and one is this. So this is called hash collision. Before that, let's summarize one more time. So the hash function h maps the universe u of keys into the slots of a hash table t 0 to m minus 1, where the size of m, m is the size of the hash table is much less than the size of the universe, because you do not need to create the table with the size of the universe, which is very large, and probably many of the keys are not actually being stored. So we do not need direct addressing. We can just create a table with as many nodes as needs to be stored, and create a hash function so that those keys can map to that different slots in the hash table. And as I said, multiple elements can map to the same slot in the hash table, and that is called hash collision. I said that if you have unlucky mapping of elements, then then the worst case chance is that all the elements of the set S will be mapped to the same slot in the hash table. Before that, let's see. Unlucky mapping of all keys into slots of table might result in collision. So this is called a collision when multiple items, more than one items, kind of hash to the same slot. So when a record to be inserted maps to an already occupied slot, a collision occurs. Okay, let's see what's a collision. So collision is, as I said, multiple items in the set S is actually being mapped. So the hash function is generating the same key value for both of them. So the hash function, the hash value of two items are actually same. Two or more items can be. So this is called collision. And when a hash collision occurs, we need to resolve it. How we resolve? There are two approaches of resolving. The first approach is called resolving collision by chaining. Okay, what is chaining? The idea of chaining is that link records in the same slot into a list. Okay, so make a linked list of all the items which hash to the same slot. Like in the slot I, this 3 items whose hash values become I. So they will all be mapped to the location I. So how they are mapped? So we create a linked list of items, okay, and then connect it with the same slot I. So what if we need to find out this item, search for this items, what we do? We first generate the hash value and we go to this location I. When you go to that location I, we start traversing this table, and then we try to, suppose we want to find 56. Then you go to the calculate the hash value, go to the location I, then start traversing this table, the linked list, and then in the second position of the linked list, we find the item 56 and return it. So this has to be traversed in a linear manner, one by one. So then what is the, as I said, what is the worst case time? The worst case happens when all the elements in the set S are actually mapped to the same slot, suppose in I. If there are 3 elements and all mapped to I, then this is the worst case. Why this is the worst case? Because then all the n elements are in the same location. So first we have to calculate the hash value to reach to that location. Then we have to, one by one move through this n elements. So if it's as the n elements are there, so it will take theta of n time to find the element from this linked list, as well as some more time to calculate the hash value. Okay, so every key hashes to the same slot. So, and the access will take theta of n time, worst case, if mod s equal to n. That means if the set size, the size of the keys is n, and all of them hash to the same location, then you have to go to that location and look through the linked list to find out which key you are looking for. What about the average case? So if we do not assume that worst case behavior, and as you know, the hash table is an efficient data structure, so we do not really look for the worst case to happen always, right? And it does not also happen always. So the average case is that there's an assumption called simple uniform hashing. What does it mean? It means that so the simple uniform hashing means that each key K belonging to S is equally likely to be hashed to any slot in T. Okay, it means that it can go to any slots, and any key can go to any slot. That's why the idea of randomization or randomized distribution of keys within code. because this is the idea coming from simple uniform hashing. So any key go to any slot, okay. So likely to be hashed to any slot in T, independent of where the other keys are being hashed. So there is no dependence from key to key. So the hash function will be operating over the key and try to find the slot, and where the previous element went, which slot, and where the next element will go, the current element has no dependence on that. Okay, so how we say that? This is a probabilistic assumption. So we say that if probability of hashing one particular key to one particular location is 1 by m, because there are m number of slots. So any key can go to any slot. So the probability is 1 by m. Now if there are n independent keys, so it will be 1 by m plus 1 by m plus 1 by m, in that way n times. So because they are independent of each other, so we added the probabilities, and finally we get the probability of n by m. Okay, so the probability of n independent keys going to the n independent slots are n by m. Now we define a term called a load factor. What is a load factor? So the load factor says the load factor of a hash table with n keys and m slots is alpha. It's called alpha, which is n by m. Okay, as I said, n by m here, this is the probability of n independent keys, hashing to m independent slots. So this is actually, now the load factor actually says the average number of keys per slot using that probabilistic calculation. Okay, so what is a load factor? Load factor is actually the average number of keys per slot. So now what is the expected unsuccessful search time for the average case? Why we consider unsuccessful? Because if it's unsuccessful, suppose there are in other slots there are other keys, and this is like the n by m number, okay, n by m, 3 keys for this particular slot. Now in the worst case, for an unsuccessful search, what will happen? We go through it and we do not find it. Only for the unsuccessful search, we search all the entire list, right? With average size is n by m. So the expected unsuccessful search time is theta of 1 plus alpha. The alpha is the load factor, okay, average number of keys. That means the length of this linked list is alpha, and 1 is the constant time to calculate the hash function. So hash calculation I'm writing just for the sake of understanding. So so first you calculate the hash value, and then you go to that slot, and then you go through the list and try to find out where your element is. For unsuccessful search, it will search the whole list. Okay, theta of 1 plus alpha. Now, if you assume that n and m are comparable, that means the number of slots in the table, which is m, is comparable to the number of elements in the set of keys, which is n, then we can have, like, it's like if n equal to m, then from here we can see the expected search time will be theta of 1. If alpha is, that is a list size, if n equal to m, then alpha will be n by m equal to 1. Okay, if it's not exactly 1, it's comparable to 1, close to 1, that's also fine. Okay, so in that case, what will be? Theta of 1 plus alpha will be theta of 1 plus 1, okay, which is also theta of 1. Here it means that this is constant time. As you know, it's asymptotic analysis, not a simple addition. So this means that it will take a constant time to go to the location and then find the element in the linked list. If the linked list size is 1 or comparable to 1 or close by 1, when the number of elements in the key is equal to the number of slots in the table. That means every element can go to 1 slot. So in that case, the expected search time will be theta of 1, which is why actually we use hash table. And in majority of the cases, we see this or theta of 1 or very close to that is the average case runtime of hashing algorithm, and that is actually very helpful for this dictionary type data operations.